C++ is weird, and pointers are a big reason why. But before we get into the deep end of pointers, let's talk about variables. This is how you define a variable in C++. Pretty simple, right? You have the type of the variable, the name of the variable, and the value stored. The compiler reserves 4 bytes of memory for integers and stores the value in that memory location. Now let's say you want to update the memory and increase its value by 1. But how will the compiler know what is A? What memory location to look at when I call this variable A? If only there was a table that maps the variable to the address it is referring to. Well, there is. It is called symbol table and it is created during compile time. So whenever a new variable is created, first the memory is reserved. Then an entry is created in the symbol table with the name of the variable. Along with that, we also need to keep the type of the variable because we need to know how many bytes we need to read. Whenever we use this variable again, the compiler can easily check the symbol table for the location in memory and do whatever needs to be done. But do you know you can actually see this memory location using the ampersand operator or the address of operator? Now, ampersand is used in a lot of different ways in C++ and it is pretty confusing. But let's just focus on the address of operator. Whenever we use it in front of a variable, as the name suggests, it gives us the address of that variable, which is usually a hexadecimal number. 0x means that everything after that is a hex number, and we can actually store this memory address in another variable. And we call this new variable a pointer. And that's what a pointer is, a variable that stores the address of another variable. And to define a pointer, you need to define the type of the variable it is pointing to and then the name of the actual pointer. And for the sake of simplicity, you can read this from right to left as P is a pointer to an integer, and it will store the memory address of variable A. Let's go back to the symbol table now. Since P is also a variable with its own memory, we need to store it in the symbol table. The only difference is that P stores memory locations instead of int, char, float or double. When we print A, the compiler usually goes to the memory location of A and prints it. But now we have the memory location of A stored as well, so we can access the value stored at A. And to do that, we can use the dereference operator, which is basically an asterisk. This is technically different from the asterisk we used while defining the pointer, but you can Google it out. We use the dereference operator to go from an address to wherever that address is pointing. So when we write *p, we actually reach the same memory location where A is stored. So what will happen if I do A++ and then print the value of *p and A? Well, the compiler will first process A++, so it will go to the location A is stored at and then increase the value by 1. Then when we write *p, the compiler will go to the same memory location because P is pointing to A and then read its value, which now will be 11. So it will print 11. And if we print A, it will also print 11. So what will happen if I write *p++ and then print A? Well, *p will update the value at that memory location to 12, and when we print A, it will print 12. So technically, *p and A are the same thing. We can update it, we can print it. Both of these lines will update the same memory location. And the value of P and ampersand A is also the same. This is the memory address of A. But what will happen if you do P++? Well, I'll let you Google that. This was a brief introduction to what pointers actually are. Pointers can be used in much more interesting ways with arrays, strings, and other objects. But that is for another video. Bye bye.